We are making our way around the hydrologic cycle. We're at a point where we're talking about a very specific flux. So in the past, we've discussed different reservoirs within the hydrologic cycle. This is a flux. So let's look at what it looks like in the hydrologic cycle. Okay, so we've talked about precipitation, surface runoff, water tables, percolation, and the groundwater system and the surface water system. What we're looking at now is this area here, the vegetation and the evaporation from soil, evaporation from reservoirs, evaporation from land, that transpiration from vegetation. So this whole flux is called evapotranspiration. What's evaporating from the surface and what is transpiring from the plants. So that's what we're honing into in this lecture, the evapotranspiration. So simplified, or just a different look at that here. This got a lot going on in this water cycle, but we're over here at evapotranspiration, where the land surface, there's water evaporating and also transpiring from the plants. Okay, breaking down that language here, evapotranspiration, the water lost to the atmosphere from the ground surface. So that includes the plants here with the ground surface. The evaporation is from the capillary fringe of the groundwater table. So the moisture that's in the soil is evaporating up and out of that soil. It's also evaporating straight from our surface waters. Transpiration occurs from the leaves of plants. So those work together to make evapotranspiration. Those plants are pulling up water from the capillary fringe of the groundwater. So just the edge of the groundwater, that moisture in the soil is coming up into the roots of the plants, through the xylem of the plants, and out the stomata of the leaves. Okay, that process is a part of the photosynthesis process, where plants take in carbon dioxide in the presence of water, in sunlight, and create sugars. They create plant matter, the matter that makes up the plants. A byproduct of that process, thank goodness, is oxygen. So here's a diagram showing it. The roots are pulling in water. The water travels through the plants and out the leaves along with oxygen as a byproduct of photosynthesis. So here's a zoom in on one leaf. Water and minerals are coming in to the leaf here. The water pooling on the leaf is water coming out of the little stomata, open pores on the leaf surface. So here's a little thought question for you. Where does the mass come from that makes up trees? Well, let's take a look at this little video. Instead of clicking that link, I'm gonna just come straight to YouTube. Too many commercials. Okay.
Trees are some of the biggest organisms on the planet. But where do they get that matter to grow?
It's nutrients out of the ground.
Just out of the soil, really, yeah.
Goodness out of the soil, I suppose.
Comes out of the soil.
Yeah.
Goodness.
Why isn't there a big hole around the tree where it's taken out all the soil?
Because it doesn't say gradually that the soil has time to recover.
Now, I think it's intuitive to believe that the tree gets most of its mass from the soil, because you can see those roots digging into the soil, and they must be taking something out of there. And I mean, a tree looks like dirt, and it feels solid like dirt, but it's not. In the early 1600s, a scientist named Johann Baptista van Helmholtz tried to figure out where the mass of a tree was coming from. So he got a pot of soil and very carefully measured the amount of soil in there. Then he planted the tree and took care of it for 5 years, making sure that no soil left or was added to his pot. And at the end of this experiment, he weighed the tree to find that it was 72 kilograms, but the mass of soil had only decreased by about 60 grams. This was pretty strong evidence that the mass of the tree does not come from the soil.
I've never thought about that, actually, because they don't really eat anything, trees.
They don't eat anything?
No.
They don't eat anything.
Water is all they absorb.
That's all they eat?
Yeah.
They don't eat anything else?
No.
That's all they eat?
Well, presumably from the water and the nutrients from the soil.
Is there anything else that you need besides the soil and the water?
I suppose that's all you need, isn't it?
To make wood?
Other than the original seed for for that particular tree, I
The
suppose.
seed and the soil and the water, and that makes this big tree.
Of course, Johann Baptista van Helmholtz did conclude that the tree was made entirely of water. Now, while that's not correct, at least he was on the right track, realizing that the matter of a tree doesn't come out of the soil.
The sun energy, yeah.
The sun energy.
Yeah.
Are they converting energy into mass, or do you know what I mean?
Yeah, I don't
Like
know.
there wasn't stuff, and then there was. Like, where did that stuff come from?
Magic. I don't know idea.
My question is, where do they get that mass to grow big?
Sun. Get it from the rain and the sun, presumably.
Light, sunlight.
And the sunshine.
The sunshine? Does the sunshine add mass to the tree?
Well, yes, it wouldn't. They wouldn't grow without it. I don't know whether it adds mass, but they wouldn't grow without it.
Of course, the sun's energy is needed for the tree to build the matter into its branches and leaves. But the sun itself, the energy, is not matter.
Well, I suppose we've got to put air into this as well. If you're, there's got to be something out of the,
What is it
a
about
gas,
the air?
a gas in the air that it needs as well.
Oxygen.
The trees need the oxygen.
Yeah, they need the oxygen, don't they?
And I guess oxygen. The oxygen, of course.
The oxygen?
Yeah.
Are there
Maybe
any
the trees.
ingredients that we're missing?
Carbon dioxide.
Carbon dioxide.
Carbon dioxide.
So would it surprise you to find out that 95% of a tree is actually
Carbon dioxide.
from carbon dioxide? Trees are
much,
largely
yeah.
made up of air.
Yeah. Surprising.
Yeah.
Yeah,
That is surprising.
I need this reaction like, holy shit.
So as it turns out, trees are mostly made out of air, out of the carbon dioxide that they take in. And what's interesting is that we breathe out carbon dioxide and water. That's how we lose mass. But it's the exact same substances that trees breathe in to gain mass. So if you can imagine a closed system where it was just you and a tree, you would breathe out that carbon dioxide and water, the tree would take it in, so you would get smaller while the tree is getting bigger. And in a sense, you're becoming the tree.
There you have it. The carbon dioxide, it makes up 95% of a tree. Okay. Check out that video if you want to see it again. There is what's called a continuum of water that goes from the very tips of the roots all the way up to the stomata of the leaves. It's a continuum built on called the vascular system. Kind of sounds similar to what we have in our bodies, and it's made up of the xylem of the plant. Remember, back to our discussion of different properties of water. Water has two properties that make it unique: the way it adheres and the way there's cohesion within the molecules. So because of the polar nature of the water, it adheres to the xylem or the cell walls of that vascular system, and the hydrogen bonds between the molecules of water hold those molecules together. Think of it like drinking out of a straw. When you slurp up water in a straw, the water all kind of sticks together, right? That's cohesion. It doesn't just fall apart as you're drinking the water. And adhesion keeps the water molecules stuck to the sides of the straw. So the vascular system of a plant is like a straw. The sucking occurs because at the surface of the stomata, see the image here, there's all those little openings where water's continuously evaporating out. So it's coming out at the stomata, coming in the roots. This process of moving water from the roots throughout the plant and out the stomata is called the cohesion tension theory, also called the adhesion cohesion theory for plants. In the hydrologic cycle, this flux is pulling water out of the soil, the wetted perimeter, that capillary fringe of the water table, and pulling it through the plant and out into the atmosphere. So again, a flux. Evapotranspiration accounts for 60 to 70% of water loss from the Earth's surface. So we have the transpiring from the plants and the evaporation of water that is stored in a tree because of interception. Trees intercept rain. right? They're in the way, so the rain doesn't make it to the ground. That water that hits the tree is evaporated. Some of it runs down the plant, but some of it is evaporated back into the atmosphere. And then there's the evaporation from soil water. Here's what interception looks like. So rain comes down, hits the tree. Some of that water is going to run down the trunk of the tree and into the ground. Some of it's going to drip, drip, drip. And then some of it's going to get evaporated back up into the atmosphere. Storage and decrease in erosion from raindrop impacts on bare soil to the processes that give us the benefit of having trees planted on like bare ground. Splash erosion occurs when raindrops hit bare soil, and that propels that soil up into the air. If it's on a slope, imagine it propels that soil up into the air, and then it falls down. That adds to what's called creep. That is the process where a hill slope, slowly over time, particles go down that hill slope. That's creep. Okay. All right. So back to the hydrologic cycle and fluxing water back and forth from the soil to the atmosphere. A small sapling might only lose between 1/2 and 1 gallon per day, whereas a really large Douglas fir tree like these can lose between 50 and 100 gallons of water a day. That's pulling it out of the soil. If we look at a whole forest, here's an acre of forest. That acre of forest during the growing season, so what do we say, April through November or October, early October, is going to pull out of the moisture 1 million gallons of water. 1 million gallons of water coming out of just an acre of a dense big tree forest. It's a lot of water. How do we measure that? How do we know the amount of water? Well, there are two ways. One, to quantify that transpiration number. We can take a plant and hook it up to this system here called a potometer. And the potometer, in one side you add water, and you're going to have a gauge, some kind of calibrated pipette, and it's going to have increments on it, and you can watch the water drop in that calibrated pipette as it goes up through the plant over time and out the stomata. So that's one way to quantify from a cutting of a plant here. Out in the field, you can set up these, they kind of look like a weather station, and they have sensors here at the top to get really good measurements of humidity and moisture in the atmosphere. And you can set those up over different forests of different species and quantify it for a forest. What is the transpiration rates of moisture in that forest? Get differences in day and night, and seasonal differences, and species differences. Okay. We'll talk about an environmental issue with these. If you change the forest, and usually a forest change is going to come from a land use change, or maybe from a disturbance like a forest fire, or in a marine environment. Maybe there's a tsunami, a marine land environment. So changes in the hydrology in the species, changes in the forest are going to change the hydrology. So different species are going to transpire different amounts. Different size plants, which is usually related to the age of the plant. A deciduous tree versus an evergreen tree. Forested versus deforested. And remember, with the forested versus deforested, there's that interception, there's transportation, and there's transpiration and also infiltration of water into the ground. Okay. Let's look at this example. Here is a small watershed. We'll say this is probably a tributary to a bigger trunk stream. And Q is the discharge out of that surface water. So it's full of evergreens. It's a cloud. It's raining into that watershed. And here, let me turn my face off so we can see, is the hydrograph. So over time, the discharge, remember discharge in the stream is a volume over time. We'll say cubic feet per second. Cubic feet per second and then it rains, there's going to be a increase in the discharge in the stream, and then over time, then they would go back to that kind of that base conditions. If we cut down all the trees now, it's full of stumps, the runoff is going to increase. The rain event is going to hit the stream faster, so it's shifted. It was here, now it's here. And the amount of water in the stream, instead of infiltrating, instead of evaporating, instead of transpiring, it's going to hit the stream faster, and we're going to get a much larger spike in the hydrograph. What does that look like? So if we think back to thinking about rivers and our conversations about discharge, what does that remind you of? Right, urbanization. So this graph here would be a pre-urbanization hydrograph, and then this graph here would be a post-urbanization hydrograph. And the main difference is just that infiltration, right? Whether or not some of that water becomes groundwater.